Welcome to the Introduction to vBlock System Management section of the vBlock Foundations course. In the previous sections of this training, you learned about the compute, storage, network, and virtualization. Now you learn about the basics of vBlock system management technology. Upon completion of this training, you will be able to describe the need for and importance of the management function in a converged infrastructure. Also, you will be able to identify and describe the purpose of each of the components of the vBlock system management technology for managing a vBlock system, including compute components, network components, storage components, virtualization, deployment, and system-level management. Let's get started with an overview of vBlock system management technology.
We talked earlier about the traditional data center and the amount of work it takes to design, procure, unpack, assemble, test, and implement a new system. However, the larger IT effort comes from trying to make these components work together throughout their life cycles. Any change to a piece of the infrastructure drives a significant amount of planning, testing, stabilization, and optimization. This iterative planning and implementing of updates using manually driven, mistake-prone procedures occurs constantly across most infrastructures, with complexity magnified and undue risk raised because of organizations being in silos. Some IT vendors depend upon IT complexity to generate services revenue from customers rather than trying to eliminate complexity. As you learned in the first module, most IT staff time and budgets are spent trying to maintain the infrastructure rather than driving innovation. In order to transform IT, a new approach is needed. VCE has pioneered a new way to create converged infrastructure, but equally significant is the way that we have pioneered new ways to maintain converged infrastructure. Among the many things that we do very well at VCE are two things. First, which we have already talked about extensively, is that vBlock systems and our engineering and manufacturing processes enable fast timed deployment. Second, and easier to overlook, is that vBlock systems are engineered to dramatically simplify ongoing customer IT operations. You've learned that vBlock systems are engineered using the best-of-breed technologies from Cisco, EMC, and VMware. One of the components that make them best-of-breed is the management tools and processes that they come with. These tools and others are incorporated into the vBlock system's strategy and approach to system management, and are important parts of simplifying ongoing customer IT operations. Now, let's take a closer look at vBlock systems management. The elegance of vBlock systems is that while their design is complex, they are engineered for simplicity in terms of operation and maintenance. They are magnificent products that incorporate leading-edge technologies throughout. VCE engineers have done the hard work of determining the best combinations of components and the best means of architecting and connecting them to produce superior reliability and performance. Service management tools make the creation and delivery of cloud services quick, reliable, and less expensive. Management tools are designed to simplify complexity by automating and optimizing responses to IT service requests, as well as provisioning and delivering of IT services. They also simplify the process of metering resource use, simplifying the tracking of the true costs of running and managing infrastructures in a shared environment. The jobs of managing IT functions and data centers are changing significantly. People want anytime and anywhere availability through the many different devices from desktops to smartphones. Quickly and with minimal effort, companies are offering on-demand IT services that cut both costs and time using network access to a shared pool of configurable compute, network, and storage resources. Management is the essential component of infrastructure as a service, which is a form of cloud computing. These convert vBlock systems from raw infrastructure into fully functional cloud computing appliances. These also enable a transformation from the traditional data center model, a hardware-intensive undertaking that takes weeks and months of IT department effort, to a converged infrastructure model with on-demand response and provisioning of needed IT that takes minutes to hours instead of weeks to months. At its core, the vBlock system's management infrastructure is designed to manage all of the components of the vBlock system as an integrated entity. It is engineered to facilitate an infrastructure-as-a-service approach to managing and automating the virtual data center with on-demand self-service, resource pooling that speeds implementation of IT services, and measured level of service for monitoring resource use. The design and operation of the management infrastructure itself is greatly simplified by virtue of the Advanced Management Pod, or AMP. An AMP is deployed with vBlock systems and is pre-architected and pre-configured to eliminate the time needed to architect the management environment. You'll learn more about AMP later. In summary, the goal of the vBlock system management infrastructure is to create a fully orchestrated management environment with low-touch management to support applications, lifecycle management, and policy-driven IT services. Before we cover the choices for managing vBlock converged infrastructures, it will be helpful to explain that to interact with information technology equipment, an interface is used. Each piece of equipment has at least one interface. Some have multiple interface options. There are three predominant types of interface that we utilize in vBlock systems. The command line interface, or CLI, is a text-based interface where commands are typed at the keyboard and results are usually displayed in plain text. The graphical user interface, or GUI, uses icons, checkboxes, drop-down menus, radio buttons, and other visual indicators and input interfaces that replace the typing-intensive process to enter commands and to navigate as in a command line interface. Interaction with the GUI usually incorporates some form of pointing device, such as a mouse or touch screen, in addition to a keyboard. When both a CLI and GUI are provided, the user's personal preference is what determines the interface that is used. The Application Programming Interface, or API, is a way to manage an environment through an application. Sometimes it is more efficient to write an application to control certain tasks that are often repeated or performed by less skilled employees. An application can consistently perform a specified sequence of steps and do so in reaction to an operator request or specific event. For example, an application could allow an operator to add predefined amounts of storage to a virtualized environment when a user requests it. The vBlock APIs are all fully documented and usable by partners and customers. Click on each link for examples and more information.
That was just an overview of vBlock system management. Let's move on and discuss the specific tools used to manage the components of the vBlock system.
Simply stated, the purpose of the vBlock system management architecture is to facilitate system deployment and system management. Some of the key functions include managing the virtual infrastructure, which involves deploying and provisioning virtual machines and virtual networks. It is also used for managing the physical infrastructure, including the technologies you have already learned about: compute, network, storage, and virtualization. Let's review some of the important management tools incorporated into the vBlock system. As mentioned earlier, the Cisco UCS Manager is the tool used to manage the vBlock system compute technology. It provides unified, embedded management of all software and hardware components in the Cisco UCS. It can control multiple servers and/or chassis and can manage resources for thousands of virtual machines. In vBlock systems using B-series blade servers and blade server chassis, the Cisco UCS Manager is installed on the vBlock system fabric interconnects. This single logical instance of the UCS Manager can manage the compute resources of several blade chassis and blade servers they contain. A single instance of the Cisco UCS Manager can manage up to 6 fabric interconnects, 24 UCS server chassis, and 192 Cisco B-series blade servers. This is a significant difference from the vBlock systems utilizing Cisco C-series rack mount servers. Recall that these systems do not contain fabric interconnects and they do not use the Cisco UCS Manager. Instead, management of compute resources in these vBlock systems utilize the Cisco Integrated Management Controller, or SIMC. SIMC, offering both a graphical user interface and command line interface, is installed on every server. It is used to manage each server individually. When compute changes are needed across multiple servers, each SIMC instance is launched and changes administered one C-series server at a time. For customers evaluating the purchase of Cisco B-series blade servers versus Cisco C-series rack mount servers, decisions can come down to the trade-off of compute management flexibility of the blade technology versus the less costly rack mount alternative. There are 2 operating systems found on Cisco switches. The operating systems are the tools used to manage networks and network switches by performing tasks like discovering, configuring, and managing network devices. The operating system installed on each switch depends on the model of switch. The first is the Cisco Inter-Network Operating System, or IOS. This is software designed for managing LAN networks and LAN switches. The Cisco IOS is used only in vBlock systems that utilize the Cisco Catalyst switch as a LAN switch. Users have the option of using the command line interface or graphical user interface that comes with IOS. The other network management tool used in vBlock systems is the Cisco Nexus Operating System, or NXOS. It contains both a LAN manager and a SAN manager, which sometimes is referred to as a fabric manager. Cisco NXOS is found on all Cisco Nexus and Cisco MDS switches. Remember that some Cisco Nexus switches can act as a LAN switch or as a unified switch with both Ethernet ports serving the needs of the LAN network and fiber channel ports for the SAN network. Each switch has a local copy of the appropriate operating system and should have a copy of the various configuration settings stored on non-volatile memory. The Cisco Data Center Network Manager can be used as a central point to configure the various settings on Nexus and MDS switches. The Cisco NXOS provides both a command line interface and a graphical user interface. The management of storage arrays is another important part of the vBlock system management. These tools provide an interface to storage arrays that are used to perform tasks such as creating storage devices and LUNs, virtual storage provisioning, managing block level and file level storage, and monitoring performance. Used for EMC vMax storage management, the Symmetrics Management Console, SMC, is an intuitive browser-based graphical interface for managing storage device performance. It is installed and hosted on the AMP and accessed using a browser from any location. Symmetrics Management Console's lightweight architecture is an ideal graphical complement to the command line interface alternative. EMC Unisphere is a simple, integrated experience for managing EMC VNX, VNXE, and vMax storage products. With functionality designed for managing both storage and virtualization needs, it's designed to provide simplicity, flexibility, and automation. Unisphere delivers a common experience with a single interface for managing file and block level storage. The VMware vSphere platform is a suite consisting of a number of software products that together enable virtualization capabilities that enterprises implement for managing a virtualized data center. Some of its underlying software products are listed here. You already learned about VMware ESXi. Recall that this is the hypervisor used to create and manage virtual machines on a physical host or server. vCenter is another product within vSphere. It provides the ability to centrally manage all ESXi hosts and the VMs they manage. With vCenter, IT administrators can centrally deploy, manage, monitor, and automate the virtual infrastructure that can span multiple physical hosts and ESXi installations. vSphere Update Manager is a plugin for vCenter Server that helps keep ESXi hosts patched with the latest updates from VMware. It can scan to identify ESXi hosts that are not compliant with current updates and can upgrade them automatically. Another tool for managing vBlock systems virtualization is EMC's Virtual Storage Integrator, or VSI. This is an optional and free add-on for vBlock systems that integrates storage management into vCenter. VSI provides visibility into the storage relationships between virtual machines and their supporting storage in a vBlock system. It shows the relationship of underlying storage configurations on the array to VMs, virtual disks, VMFS, and NFS data stores. VSI is a monitoring tool and does not provide any other system management functionality. EMC PowerPath VE automates and optimizes data path pools in virtual environments to ensure business process availability, performance, and the ability to scale out mission-critical applications. It implements multipathing for EMC storage devices and also supports dynamic I/O load balancing. It automates failover and recovery, which removes the threat of application disruptions from adapter and cable failures. When a failure occurs in the path from a host to a storage device, PowerPath VE automates the process of failing over to alternate data paths. Using intelligent dynamic path testing, it also identifies broken or damaged paths and removes them as alternatives for communicating between hosts and storage devices. It does this automatically with no user intervention, and it does so without disrupting host applications. PowerPath VE also optimizes load balancing by eliminating I/O bottlenecks in virtual environments. It assigns all devices to all paths and automatically adjusts I/O path usage to changes in I/O loads coming from virtual machines. Bottlenecks are managed by routing communications to paths with less traffic, thus optimizing load balancing in the system. PowerPath VE runs on the ESXi host, but but is managed by a remote power path server supporting addition and deletion of paths and setting multiple pathing and load balancing policies for storage devices. VCE Vision Intelligent Operations enables and simplifies converged operations. The software acts as a mediation layer between vBlock systems and data center management tools, dynamically informing those tools about vBlock systems. It delivers intelligent discovery to provide a single objective perspective on vBlock systems. Comprehensive awareness of the industry-leading components that comprise vBlock systems promotes infrastructure standardization through automated validation and system assurance. And integration capabilities make it possible to provide this level of intelligence to any toolset. The software is integrated with VMware Virtualization and Cloud Management portfolio, and also supports API-enabled integration into other standard industry tools. The VCE Vision Intelligent Operations software suite provides an integrated set of software products for managing a converged infrastructure. The VCE Vision Suite is the first software suite to provide an intelligent solution for managing operations in a converged infrastructure environment. These tools enable and simplify converged operations by dynamically providing a high level of intelligence into a customer's existing management toolset. With VCE Vision software, which is pre-installed on vBlock systems, customers can continue using the data center management tools already integrated in their data center management strategies. The software acts as a mediation layer between vBlock systems and data center management tools, dynamically informing those tools about the vBlock systems and their statuses. The VCE Vision Suite enables VCE customers and third-party developers to know the vBlock system's vital information. It reports on the health or operating status of the vBlock system and reports on the compliance of the vBlock system to a VCE release certification matrix. The software allows for intelligent discovery by providing a continuous, near real-time perspective of system compute, network, storage, and virtualization resources as a single entity, ensuring that management tools reflect the most current state of vBlock systems. Think of VCE Vision Intelligent Operations software as a layer above the element managers built into each of the best-of-breed technologies that constitute the vBlock systems. Vision Intelligent Operations combines the output from those element managers to provide a single log plus compliance data to facilitate management and automation tasks. EMC Unified Infrastructure Manager, UIM, is used to reliably automate the error-prone and tedious tasks that are required to provision a vSphere cluster. These tasks include provisioning storage, zoning SAN fabric, creating UCS service profiles, installing vSphere, and setting initial configuration of the vSphere cluster in vCenter. UIM also continually validates the vBlock and all of the resources it has provisioned for compliance with established standards. The service catalog in UIM is the foundation for dynamically provisioning and revising the infrastructure as needed. UIM integrates with a number of tools such as VCE Vision Intelligent Operations, vCenter Operations, and tools from various third-party application providers. The REST API can also be used by customers who wish to write custom applications to manage the vBlock. There are two parts to UIM, the Provisioning Center and Operations, referred to as UIMP and UIMO respectively. The two parts reside in two separate VMs, usually located on the vBlock management pod that we will describe in a moment. UIM Provisioning Center is the base software with compliance checking and provisioning automation. The Operations section adds root cause analysis and log and event correlation features to simplify troubleshooting. UIM can also be used to prepare blades for bare metal installs by configuring the resources but not installing an operating system or hypervisor on the blades.
The AMP, or Advanced Management Pod, is a critical part of managing vBlock systems. While we'll talk about this more later, let's take a look at some details here.
The AMP provides distinct separation of the vBlock system and its managing components. That means that management traffic in the vBlock system is separate and does not interfere with user workloads. The separation provides flexibility for managing upgrades and system recovery. It also enhances security. The AMP's dedicated hardware includes Cisco C-Series rack mount servers running VMware ESXi, Cisco LAN switches, and for storage in more powerful AMP configurations, the EMC VNXE storage array. Most of the vBlock system's managing software is installed on the AMP. This includes EMC UIM, VMware vSphere components, Cisco Nexus 1000V virtual network switch, and EMC storage management tools. There are two AMP configurations, a mini AMP and a high availability AMP or HA AMP. We'll talk about these next, but be aware that these will eventually be replaced with a new vBlock system management infrastructure, providing a broader range of options with greater flexibility and customization to meet customer needs. The Management Infrastructure, or MI, is the emerging standard for vBlock system management and is introduced with the vBlock System 340 and will expand to other models over time. The mini-AMP consists of a single server which boots the ESXi hypervisor from local drives. It is a basic out-of-band management environment. Out-of-band management involves a dedicated management tool for managing servers and other network equipment, whether the device is fully functional or not. It is built with a set of core management systems installed on virtual machines created specifically for management software. The AMP is utilized during the logical configuration of the vBlock in the factory. The HA AMP, or High Available AMP, is a two-server system using local disk to boot ESXi. These servers share storage in the form of an EMC VNXE array that facilitates making the virtual machines more highly available. Like the mini-AMP, it is built with a set of core management systems installed on virtual machines created specifically for management software. Some vBlock system converged infrastructures have a Logical Advanced Management Pod, or LAMP, which places the functionality of the dedicated hardware AMP onto a portion of the vBlock system that might perform production functions in addition to management.
This is a learning check that provides an opportunity for you to assess your progress. Each question provides feedback to help you remember the content, and a score is provided at the end so you can assess how you are doing. This is not a test and is not part of the certification assessment. Learning check scores are not retained in your records. However, completing these learning checks is great preparation for the certification assessment that comes later. You may This is a learning check that provides an opportunity
Congratulations! In this section, you learned about the need for and importance of the management function in a converged infrastructure, and about the purpose of each of the components of vBlock system management technology. In the next part of the training, we're shifting focus to the specific vBlock system platforms and models. Welcome to the Introduction to vBlock System Virtualization section of the vBlock Foundations course. Recall that vBlock systems are composed of compute, network, storage, virtualization, and management technologies. In the previous section of this training, you learned about the compute, storage, and network. Now you'll learn about the basics of vBlock system virtualization technology. The objectives for this section are listed on this page. Upon completion of this training, you'll be able to define and explain the benefits of virtualization in an IT environment. Describe each of the following: compute virtualization, storage virtualization, and network virtualization. You will also be able to identify and describe the purpose of each of the components of the vBlock system virtualization technology. In this section, you'll learn about the basics of virtualization, and here we'll spend significant time discussing compute virtualization.
As an IT concept, virtualization is a growing practice used by data centers to source, provision, and manage IT as a service. Virtualization can be a confusing concept to understand. So here we will take a couple of moments to define it, use scenarios to show how it can be implemented, and also to contrast it with the use of traditional physical computers. Click on and review the contents of each box to the left to learn more about these basic virtualization concepts. First, let's describe virtualization. Virtualization is a technology that allows a physical resource to be divided into a number of virtual devices that can behave like and perform the same tasks as a physical IT device. Applied to compute, virtualization is the process of dividing the physical resources of a computer, things like its memory and processor, into separate virtual computers that can perform tasks just as a physical computer does. The first scenario in our comparison is a traditional data center with exclusively physical computers used to host applications. The marketing department's applications may run on one physical system, the finance group's applications on a second, customer service applications on a third, and so on. Think about it. The number of physical computers and the space and other resources needed to operate them can be significant. Now understand that most applications never come close to fully utilizing the physical servers or hosts that they run on, in part because upgrades of hardware in traditional data centers is so disruptive that users often implement oversized systems. Managing data centers this way results in significant amounts of underutilized IT resources. The reality is that organizations are paying for significant amounts of IT resources that they never use. When we virtualize these applications, several applications running on their own virtual machine can run on a single physical server or host. Each runs their own unique operating system, and they are managed so that there is no interference between virtual machines operating on the same physical host. One virtual machine can freeze or crash on the physical host, and it won't affect the operation of the other virtual machines and applications running on that same physical server. It is also possible to resize virtual machines and relocate them to another physical host with little or no disruption. Running applications on dedicated physical hosts can be expensive on many levels. In our scenario, all of the marketing, finance, and customer support applications can run on their own virtual machines, all residing on a single physical host. The benefits of running virtual machines over the traditional physical servers includes more fully utilizing physical hosts and purchasing and managing fewer physical hosts. In addition, running fewer physical hosts mean not only reducing spending on the hardware and software, but it also affects spending on power, cooling, and floor space in the data center. An added benefit of virtualization is the inherent ability to move virtual machines from one host to another quickly and easily. This provides opportunities to balance the load across multiple host computers and to quickly restart a virtual machine on a new host if the host it is running on fails. There are real differences in how the resources of a physical computer are managed versus those of a physical computer running virtual machines. In a traditional physical computer, the operating system directly manages the hardware resources. Multiple applications can be loaded onto an operating system, and requests from applications to the system hardware components to perform tasks are managed by the operating system, which controls and directs the system's physical resources. In a physical computer running virtual machines, a hypervisor is used to create and manage the virtual machines. In vBlock systems, the operating systems are loaded on each virtual machine and control only the hardware that the hypervisor has assigned to that virtual machine. The operating system still directs hardware to perform tasks requested by applications, but it can only control the hardware resources that the hypervisor has assigned to the virtual machine. The role of operating systems versus hypervisors can be confusing, and some people mistakenly refer to hypervisors as an operating system. But it is important to know that they are not the same and they do different things. Traditionally, an operating system is loaded onto a physical server and applications are loaded onto the operating system. When an application needs to complete a task using a hardware component, like sending a file to storage, printing a page, or performing a calculation, the operating system provides directions to the hardware and coordinates completion of the task. In contrast, the hypervisor is software that is loaded onto a physical computer prior to the operating system and applications. It is used for creating and managing virtual machines on the server. The hypervisor securely partitions and controls a computer's physical resources to ensure that each virtual machine has and controls the resources that it needs. Once a virtual machine is created, an operating system is loaded onto the virtual machine. In effect, the hypervisor makes it appear that each operating system is running on a dedicated physical server, while in reality they are running in a virtual machine that can run alongside other virtual machines, sharing the resources of a single physical host. It is worth noting that there are also hypervisors that are loaded as applications running in operating systems. These are sometimes referred to as Type 2 hypervisors. VMware's Workstation is an example of a hypervisor that runs in an operating system. Workstation permits multiple operating systems to run on a single PC, but it has a number of limitations that it inherits from the operating system that hosts it. Because Workstation and other Type 2 hypervisors are generally not a good fit for vBlock systems, we will not discuss them further in this training. But you can click on the link or visit the VMware website to learn more about some of the other options for hosting VMs on an operating system. Remember that a virtual machine functions as a computer in every way except that it is not a physical computer. Each virtual machine thinks that it has complete control of hardware components like CPU, network card, memory, and storage drives. But in fact, what they control is a portion of the resources in the physical computer. Every virtual machine has its own operating system, which manages its virtual components. Each virtual machine can use a different operating system, such as Windows or Linux. That means that on one physical computer, multiple operating systems can be running at the same time. Also, some applications are designed to work well together on a single computer, and others prefer isolation. Just like on a physical server, multiple applications can be loaded onto a single virtual machine, or they can be installed on separate virtual machines, and each virtual machine can be sized to precisely deliver the optimum performance and efficiency. In this graphic, there are 3 virtual machines running on one physical computer. and the virtual machine in the middle has two applications running on the operating system of one virtual machine.
So far, we've focused on compute virtualization. In this section, you will learn about the basics of storage virtualization.
Like compute virtualization, storage virtualization can provide significant functionality that minimizes system costs and simplifies the process of managing storage needs. Click on and review the contents of each box to the left to learn more about storage virtualization concepts. In a block, before creating, when you learned about in terms of the benefits of virtual storage overall, customers achieve.
In this section, you'll learn about the basics of network virtualization.
Network virtualization involves logically segmenting or grouping physical networks into discrete logical entities called virtual networks and making them behave as single or multiple independent networks. Network virtualization allows multiple virtual networks to share physical network resources without leaking information between them. A virtual network appears as a physical network to the nodes or devices connected to it. Network traffic within a virtual network does not propagate or appear to any node that is on the same physical network but not part of the same virtual network. This enables functional grouping of nodes with a common set of requirements into its own virtual network, regardless of the geographic location or physical network of the nodes. Network virtualization involves both virtualizing the physical network and managing the virtual networking that exists between virtual machines residing on the same host. You will learn more about this later, but for now understand that virtualizing the physical network includes virtualization of network components like network adapters, network switches, and routers. Network virtualization encompasses all of the interconnectivity of both physical and virtual resources. Within physical hosts running multiple virtual machines, there is a virtual network managed by the hypervisor and including one or more virtual switches. The virtual switches provide network connectivity between VMs and can connect to the physical network to allow communication with other devices. In a simple LAN, all of the devices connected to a switch are able to communicate and share with all of the other devices connected to the switch and also to devices connected to other switches in the LAN. This is useful but has some potential problems. The two most notable potential issues are performance and security. There are some types of network messages that are sent to every device on a LAN. These are called broadcast messages. These messages are ignored by devices that do not need to process them, but use up some of the available bandwidth of each device. The security issue comes from the fact that shared resources are usually visible to all devices on the LAN. Although security measures can make the data reasonably secure on a LAN, when malicious users are able to see a locked resource, they have an additional opportunity to attempt to overcome the security. Using multiple switches that are not connected to each other creates multiple independent local area networks. These separate LANs address the two previously mentioned problems, but at the cost of additional hardware and the power and cooling that it consumes. To address these potential issues, we can use a virtual local area network, or VLAN. The VLAN is a way to restrict network traffic to specific ports on switches. Broadcasts in a VLAN will not appear on ports associated with other VLANs, and the devices on one VLAN will not be accessible from devices on the other VLAN, even if there is no security in place to lock the resource. In a network, physical computers are connected to each other and to other network resources. The network connectivity for each computer is provided through its network interface card, or NIC. Network switches are among the other components on the network. You learned earlier that network switches manage traffic among components as data passes through the network. Virtual machines must also connect to the network. Inside the physical computer, each virtual machine has its own virtual network interface card, or vNIC. These VNICs provide connectivity to the VM and connect to the network through a virtual switch that manages traffic to the physical NICs that are part of the host. These virtual switches function like physical switches, but they are software loaded onto the physical computer. Virtual networks can be created that include both virtual and physical network resources and can span across physical computers. In this example, there are two virtual networks. Notice that VM1 and VM3 are part of VLAN A, and VM2 and VM4 are part of VLAN B. Despite the fact that they share network resources like virtual switches, NICs, and physical network switches, they are discrete virtual networks. As discrete networks, the data in each network is secure even though traffic from both networks travel over some of the same network components. In this diagram, we have been describing standard virtual switches where the virtual switch on each host is configured individually. In environments with large numbers of hosts, this manual configuration can become tedious. So vSphere also supports a distributed virtual switch which spreads the functionality of a single virtual switch over a number of hosts. The virtual switch on all of the hosts sharing one distributed virtual switch is managed simultaneously when changes and additions are made to the configuration, such as adding a VLAN. Port channels are a way to virtualize two or more physical ports into a single logical port. The bandwidth of the ports is sometimes combined, and port channels provide alternate paths in case a physical path fails. The algorithm chosen determines how the port channel behaves in various situations, and the number of options available depends on the model of switch and network interface cards used and must be configured the same on both the switch and interface cards. There are many reasons why port channels are a way to virtualize two or more physical ports into a single logical port. The bandwidth of the ports is sometimes combined, and port channels provide alternate paths in case a physical path fails. The algorithm chosen determines how the port channel behaves in various situations, and the number of options available depends on the model of switch and network interface cards used and must be configured the same on both the switch and interface cards. A convenient way to think of a port channel is as a multi-lane highway. Vehicles can travel on each lane of the highway, and if traffic flow is interrupted on one lane, the traffic is diverted onto the other lanes. There are many reasons why companies use network virtualization. Here are a few. One important benefit is security. Despite the sharing of physical network resources, virtual networks restrict access to the devices on it and can isolate sensitive data flow to only the components on the virtual network. Network virtualization can also enhance performance by restricting physical network broadcast communications from a virtual network, which eliminates some of the network traffic and improves performance. And by enabling multiple virtual networks to share the same physical network components, it increases equipment utilization. This decreases the need for constructing separate physical networks and reduces cost.
Now, with an understanding of virtualization across compute, storage, and networking, let's discuss the vBlock system's virtualization components.
The vBlock system virtualization technology includes these components: the VMware ESXi hypervisor and the Cisco Nexus 1000V virtual network switch. We'll talk about each in turn. VMware ESXi is the industry-leading hypervisor that provides a server virtualization solution. Remember that a hypervisor abstracts CPU, memory, and storage resources so that multiple virtual machines can operate concurrently on the same physical server. It is used to create and manage virtual machines on a physical host. The physical host on which VMware ESXi software is installed is called an ESXi host. The ESXi hosts provide physical resources used to create and run virtual machines. ESXi is part of the VMware vSphere virtualization platform that is part of vBlock systems. Click on the link to access more information on vSphere. The Cisco Nexus 1000V series distributed virtual switch is designed for virtualized environments. Cisco Nexus 1000V switches are implemented in most vBlock systems. The switch has the same Cisco Inter-Network Operating System, IOS, found on many other Cisco switches, which allows customers to leverage management utilities and network administrators' familiarity with the command set for network management.
This is a learning check that provides an opportunity for you to assess your progress. Each question provides feedback to help you remember.
Congratulations! You've completed the Introduction to vBlock Systems Virtualization. In this section, you learned about the benefits of virtualization in an IT environment, vBlock system virtualization including compute, storage, and network virtualization, and you also learned about the components of the vBlock system virtualization technology. In the next section, you will learn about vBlock system management.